morning, everyone. We are going to be working and finishing applications of Taylor's series. That's my goal, at least. I have made a change. It's a little change, but it will help. The questions or the exercises, question 1 aren't really fair. So I've just made question 1 worth 0 points. That way you can play about with the applications and move the little sliders and see what the functions look like without having really to do the questions. So if you don't even do the questions, you're going to get 0. If you do the questions and get them right, you're going to get 0. And if you do the questions and you get them wrong, you're still going to get 0. So I don't like the questions that was brought to my attention. I thought they showed you the error, so you would just read off the answer and write it down, but evidently not. So that's that guy. So let's get started on my first example. I've lost a place here. I'm not sure where the heck I am. Where's my little, where are you guys? Oh, here you are. What are you doing over there? Come over here. One of my little windows was in the wrong place. Okay. So, there we go. Well, most questions involve 2 things. One of them involves finding an estimate of the maximum area using a Taylor's polynomial, Tn. And this is the general formula that we're going to use. So this one is question 3. The function that we're going to deal with is the square root of x. It's centered at 4. We're going to do 2, which is a Taylor's 2. And for some reason, the x's are going to be chosen in the range 4 to 4.7. Question A asks us to find that guy. To remind you what these guys look like, it's f of a, the derivative of a, x minus a over 1 factorial, plus the second derivative of a, x minus a squared over 2 factorial. That's what T2 of x is going to look like. So to be able to do that, I need to find the value of the function a, the derivative of a, and the second derivative of a. Now, I don't need to do any general version, so I'm not even worried about that. That's the first guy. So f of a is going to be the square root of a, which is 4, and that's 2. So basically, I should have called that as a 4. The first derivative is 1/2 x to the negative 1/2, which I'm now going to call that guy. And the first derivative at 4 then is that, which is 1/4. And then the second derivative, well, multiply by the power and reduce the power by 1. But that's not very pretty. So I'm going to turn it into 1 over x to the 3/2, which is this fella. And that way I can now find the second derivative at 4 as an exact value, I hope. It's going to be that guy. 4 cubed is 64, square root of 64 is 8, so that becomes negative 1/16. So I now know who T2 of x is. It's f of a, which is 2, plus f dashed of a, which is 1/4, x minus a over 1 factorial, plus the second derivative, which is this fella, x minus 4, x minus a squared, over 2 factorial.
Question?
Yes.
The 4 outside of the square root turned into 2. Why?
Whoa, what happened to that? Well caught. No idea why I did that. Right, that mess there says 32. Okay, I was going to make it tidy anyway, so I can do that now. That's 2. 1 factorial is just 1, so I'm going to leave it like this. 2 factorial is 2. That means that gets doubled up to 64. And we are done as far as T2 of x is. So it's this polynomial. Are you comfortable about the process, missing out the little mistake of how to do that, right? You basically just keep finding 1 derivative, 2 derivative. Now, if they'd asked me for T3 of x, because they could have, wouldn't I just do another line, find the third derivative at x, evaluate it at 4, and that would give me the next number in the list, and the next number in the list would be the third derivative at a, x minus a cubed over 3 factorial. So you just repeat the process, in this case, until you reach the second derivative. And that's what it looks like. You do not do anything else to that. So don't worry about foiling this out or collecting like terms. We typically do not do that. That's the final answer. And that would be part A. And that's very common in these questions, that you'll be asked to find a T2 or a T3. Right. Any questions about that process? Just what we did. We good? Now, these are quite time consuming. This is a very simple function. Can you imagine what it might be like when it's x cubed sine x? You know, you might have a lot more work to do. But it's the process will stay put, just the amount of work involved might change. Now, part B is a little bit trickier. This function here is a remainder or error function, as I prefer to call it. And it tells you the maximum error that you're likely to get. And for a T3, the error is called R3. And for a T2, the error is called R2. And it's equal to the nth derivative plus 1. So you add 1 more to the derivative, evaluated at a, x minus a to this guy over that, with one extra little bit. It's the maximum value of these terms. Okay, so in my question, this fella, we're being asked to find the maximum value of the remainder function, which means I have to do the third derivative evaluated at x. So let's find out who the third derivative is. Should put a little x in there. Well, just to remind you where we left off, this is the second derivative. The third derivative is multiplied by the power, which gets me positive 3/8, and reduce the power by 1, right? I want to make that look pretty. I won't be able to do very much. So that should have been an x. Now, what's the maximum value of this? Well, you only pick values of x in this question from 44.7. Almost always, you will get the maximum value at one of these endpoints, right? 99% of the time. Now, if I plug in 4, it'll give me a number. If I plug in 4.7, it'll give me a number. Whatever one of them is the biggest, that's going to be the one I'm going to use. Can you look at those two numbers and predict which one of those two I should use to get the biggest answer so I can cut down my workload by half? If that's a 4 or a 4.7, which one of those two choices would make that fella there biggest?
4.
Agreed. Because small on the bottom means big answer, right? So here it goes. Essentially, I'm going to find the third derivative at 4. Now that's the square root of x to the 5. I could just find the square root of 4 and raise it to power of 5, which is nicer. So let's see what that looks like. Okay. 3 divided by, put a bracket around it, 8 times 2 to the power of 5. And I get 0.011718775. Or if you're really using it, it's 2, 4, 8, 16, 32. It's that guy if you want to use a fraction. But the whole thing's going to turn into a decimal anyway, so that decimal will do. Okay, so that's the bit that goes there. Right, I've got an x minus a to the n plus 1 now. And I need to find out what its maximum value is going to be. And I should say 4 in this case. And what's the maximum value going to be? Well, same thing. Won't the maximum value happen at one of the two endpoints? So x minus 4, I'll keep putting n plus 1 because I'm looking at my general formula, is going to be cubed, right? So x minus 4 cubed. That's what the x minus a to the n plus 1 is about. Okay, what's its maximum value? Well, either happens at this number or at this number. Would you agree at this value of x, you get 0, so it must be at this side. So its maximum value is 4.7 take away 4 cubed, which is 0.7 cubed, which is also going to be a horrible decimal, 0.7 cubed. And I got 0.343. So that's this bit. So in my formula here, I'm looking for that guy. He's the third derivative maximum value. He's x minus 4 cubed maximum value over 3 factorial, right? All these guys are 3. This guy is him. This guy is him. And 3 factorial is 6. So here goes. 0.01171,875 times this fella, 0.343 divided by 6. And I get the answer 6 point, oh, how accurate do they want this? Good grief, 6 decimal places. Okay. 6.6992187 e to the negative 4. That's what that says. Okay, you want 6 decimal places out of this. We have to figure out how to write this guy as a decimal. 0.123. That's essentially what this means. It really actually means that. And then 1, 2, oh, darn it in space. Technically, isn't that the 6th decimal place? But don't you round off? And unfortunately, that number is big. It's also a 9. So what will round off then? Well, this question, this guy at the end rounds off. Are you happy about why there is a 670 at the end? It's just a weird, unfortunate that the last digit was a 9 and it rounded up. Okay, so these are very time-consuming questions, right? But at least they're all pretty much the same question. So, anything about that one before I start the next one? Okay, take that as a good sign. Next one, question 4. This is a function It's going to be centered at 0. That's good news. That should make it a little bit easier. N equals 4. That's bad news because that's an ugly number. And the x's are going to be between 0.8, negative 0.8, and positive 0.8. And we are going to find that guy and that guy. Same two questions as before. Let's see what happens. Here's my first function. If you evaluate it at 0, the answer is 0. If you want to do the first derivative, you call this guy f and g, and you will use the product rule. If you evaluate the first derivative at 0, that gets you 0, and that gets you 0. Oh, another 0. To get the second derivative then, differentiate that guy, you get cosine x. This guy's going to need a product rule. So what do I get? I get 2 cosine x's, take away an x sine x. And the second derivative evaluated at 0 is 2. Okay, third derivative. Two sine x. Do another product rule. If we call this negative x, might make my job a little bit easier. I'm not really doing, I think, anything particularly hard. I'm just doing lots of stuff. So what do I get? I get negative 1 times a g plus a negative x times a cosine. What does that get me? It gets me 2 sine x, take away sine x, minus an x cosine x. So I get sine x, take away x cosine x, and I get a third derivative at 0. Oh, goodness gracious me.
Quick question, should the 2
Yes.
sine x be negative?
Should this
That's what I
2
was
sine
gonna
x?
say.
Oh, thank you. Well, that's going to change this a little bit nicer. It's still going to make that 0, but at least it's accurate. Right. Quite kind of curious here. Do you see that this ends up being an awful lot of the terms are going to be 0, aren't they? Okay, it is what it is. Right, I need one more. I'm just going to rewrite the third derivative up here, just so that I know I'm starting at the right point.
You're on the fourth derivative, right?
Yeah, because I need one more derivative, right? So I've just rewritten the third derivative again. So if you differentiate this guy, you get negative 3 cosine x's. If I call this f and I call this j, I get, yet again, another one of these. This guy is negative 1 times a cosine x plus a negative x times a negative sine x. Let's see where this is going. Negative 3 cosine x's. Take away a cosine x. Add an x sine x. And evaluate that guy also at 0. Oh, well, negative 4 cosine x's plus this guy, I guess. Right, now I can do it. And you get negative 4. So out of all that hard work, I'm just doing a summary here. F of 0 is nothing. The first derivative at 0 is nothing. The second derivative at 0 is 2. The third derivative at 0 was 0 again. And lastly, the fourth derivative at 0 is -4. So when you do t4 of x, you're basically going to do all the terms up to the fourth derivative. So it's going to be the value of the function at 0, the derivative at 0, x over 1 factorial. Because we're centered at 0, I don't need to write x minus 0 all the time. It's the same as x. Then it's going to be the second derivative at 0, x squared. Then it's going to be the third derivative at 0, x cubed. Because we're doing t4, we go as far as the fourth derivative at 0, x to the 4 over 4 factorial. This guy is 0 plus this guy is 0 plus this guy here is 2. So you get 2 lots of x squared over 2 factorial. This guy is 0. And this guy was -4. So you get -4 x to the 4 over 4 factorial. And this fella here is 2, and it cancels out with that 2, so you get x squared. And this is -4, and that guy there is 24, so you still get 6. So you get -1/6 x to the 4. And you have now got that guy. Are we cool with the process? It's quite mundane after a while. But we got the guy they're looking for. Now, the second part of that question, of course, is going to be the maximum value of this fella. So I need to know the fifth derivative, x to the 5 over 5 factorial. And x is going to be in this question between -0.8 and +0.8. So I need to know what the fifth derivative is, and then we can figure out what the maximum value of each of these pieces is going to be. So I'm going to have to take the fourth derivative, which is this guy. And I'm going to have to find out what the fifth derivative is. Okay. Well, that guy there is going to get you -4. You're going to get a sin x. 2 negatives make it a plus. And we're back to another product rule. So I get +4 sin x. 1 times sin x. Add x times cosine x. So it looks like I'm going to get 5 sin x's plus an x cosine x. Now I want the maximum value. Now the maximum values tend to 99% of the time tend to happen at the extremes, right? You agree? That's where we should look. So I'm not sure how these two are going to play together. So if I'm not sure, I'm just going to evaluate both. Right. So I'm basically going to find what that derivative is at -0.8, and then what the fifth derivative is at 0.8, which is this fella here. And that's definitely what calculators are for, right? So I'll do this one here. It's 5 times the sine of 0.8, add 0.8 times the cosine of 0.8, and I get 4.144145 5.822. And if I do the one above it, I get 5 times the sine of negative 0.8 plus negative 0.8 times the cosine of negative 0.8. And this guy ends up giving me, oh, negative 4.144145.822. Now I'm interested in the maximum value, but technically there's an absolute value around this. So I don't care if the number is very big and positive or very big and negative. We lucked out here. Aren't both of these the same number, even though the one's plus and minus? So this is the maximum value, right? Where's my little guy hiding? Yeah. So this is the maximum value of that piece. So it's going to be 4.1, a lot of 4s, a 1, 4, 5, 8, 2, 2. 5 factorial, you just have to check that, but it's 120. Right, I just need to find out what this guy is in this range. Would you agree that the biggest number might be happening somewhere at the end, right? So how about 0.8 to the power of 5? 0.8 to the power of 5, and it's 0.32768. If you tried the other endpoint, you would get negative 0.3768, so it wouldn't really matter. So this guy here is nothing 0.3768. Right, you put that package together, let's see what we got. 4.144145822 times 0.3768 divided by, yes,
According to my calculator, it's 32768.
327. Okay, I can fix that, I think. 32768 divided by 120. Hit the button. Oh shoot, you couldn't do it that way. What did I screw up? I'll just have to redo it. Not my favorite thing to do. 144145822 times 0.32768 divided by 120. Oh God, this is not my day. My battery finally died on me. Has anybody done that calculation for me? Otherwise, I'm going to pretend it's 42.
I got 0.011316281.
0.0
11 316281.
Okay, now they want it to 4 decimal places, which means we're going to stop 1, 2, 3 here. Okay, so the answer is 0.0113. And you now have the maximum error. Now, what does that actually kind of mean? Because it's hard, it's easy to lose track of what we've got. Suppose I was interested in x sine x. I could use this polynomial, t4 of x, instead of that guy. As long as I use values of x in the range 0.8 to negative 0.8, plugging into here will give you the similar answer to this. And the worst case scenario is that the biggest error is 0.011. Very roughly, doesn't that mean that this guy is good to 2 decimal places? So as long as you stick to values of x between here and here, you can use this quadratic and get the same answer is x sine x to about 2 decimal places. And in a lot of times, a lot better than 2 decimal places, right? That 2 decimal places is a guaranteed worst case scenario. Most of the time, it won't even be anywhere near as bad as that. So that's kind of what we're doing. We're finding this fella, and then we're trying to find the maximum error, right? How good is it, right? Can you imagine I've got a totally different question? And that ends up being the polynomial, right? If I tell you that the maximum error function, oh, let's say you're using x in the range 1 to 0, right? If I tell you that the worst error that you get here is that guy, aren't you pretty comfortable about using this for the function? It's going to be really good. You're pretty sure about the first 3, not so keen about the 4th decimal place, really good. On the other hand, I get that error. Do I really want to use this polynomial when I can't even guarantee the first decimal place? And so knowing this, doesn't it give you some kind of confidence on how useful the particular Taylor's polynomial that you've got in front of you? Yeah. Could I use it? Can I be comfortable that it would give me decent answers? Yeah, no. Now I could improve that. Couldn't I do a T40 in that, and then this number here would go right down? Some functions, their Taylor series doesn't need to be that big, right? You can do a T3 on them, and they're pretty good to, 4 or 5 decimal places. Some functions. Other functions are horrible. If you tried to use a T4 on it, you'd be lucky if you get the whole number part right. They're that inaccurate, right? And so without this analysis, we can't really tell. You can't just say, well, I'll wing it. I'll hope that the T4 I'm using is going to be good, because that's how bridges fall down, right? These questions are taking a horrendous amount of time. I'm seriously considering reducing the number that you need to do, because this is my opinion, hopefully you agree. Would you agree it's really just a process that you just do over and over again, right? So if I'm going to do one more, and then I'm going to cut back on the number of questions that you need to do in homework, because I don't want to spend, forever in a day. If you spend half an hour on each question, can you imagine 8 questions is 4 hours? That's a lot of work that you could do more usefully doing cleverer stuff. So who am I picking? I don't know who I'm picking. I'm randomly scanning through this. Let's do a log for my last one. Actually, that's a good idea. I will be finishing this homework on question 6. So when you leave, I'll just take the other questions out. And if you want more practice, I'll just put them in and call them zeros. That way you can play with them and try them out. But right now, our last guy in town is this fella here. It's going to be centered at 2. It's going to be a 3 guy, and we're going to use it in the range 1.5 to 2.5. Okay, I'm going to keep that guy there, and I'll start my workload. Since it's that fella, when we're finished, isn't it T3 of x? Right. And so I should put it a bit lower. That means we're going to find f of a, the first derivative, the second derivative at a, and lastly, the third derivative at a. Right. Okay, so now I know where I'm going. it's the natural log of 1 plus x. So the value of the function at 2, that's what f of a is the natural log of 3. Okay, first derivative. If you differentiate this guy, you get 1 over 1 plus x. The first derivative at 2 is a third. That wasn't too bad. Second derivative. Okay. If you want to differentiate this fraction, what would be a better way to write it down? I mean, I could do the quotient rule if you want, but I'd prefer not to.
1 plus x to the negative 1.
Yeah. Now, if you write it this way, you can just basically do a chain rule, which is multiply by the power and reduce the power by 1. And then for calculation purposes, it's probably a better idea to call it that. So the second derivative at 2 is negative 1 over 3 squared, which is 9. Okay, we just need to do the third derivative, which means I'm going to call it that guy first. Oops. I'm going to call it that guy so that I can get third derivative, which is positive 2, 1 plus x to negative 3. So it's positive 2 over 1 plus x cubed. And the third derivative at 2 is 2 over 27. And since I'm going to be doing the R4 guy, although I'm not going to use it here, I am going to use it later. So if we think about the third derivative, which is this guy here, I need to find out what the fourth derivative would be. And that's going to be what? Negative 6, 1 plus x to negative 4, which I'm going to call that guy. Right, I don't need him right now, but I will need him later. Okay, we've got all the pieces. Let's put them in, see what we get. T3 of x is going to be the function evaluated at a, so that's log 3. Plus the first derivative, which is a third, x minus 2 over 1 factorial. The next derivative is a ninth, x minus 2 squared over 2 factorial. And the last one is 2/27ths, x minus 2 cubed over 3 factorial. So it's going to be the log of 3, 1/3 of this guy, negative 1 over 189. So you get that guy. 3 factorial is 6. 6 will cancel part of that and leave 3. So I end up with, I believe, 181. And
Wait, why
Yes.
did he get 189?
189. It's not 21. It's 2 factorial.
oh, darn it, it's 2 factorial, which is easy to fix because it's now 18. Oh, and that's 3 factorial, which is 6, which is correct, which cancels with the 2, leaves the 3 behind, that's 81. So 18 and 81, we are finished with the T3 of x part, right? Is it slowly getting the format to it? This is what you do, you get all the pieces, you stick them all together, and you try and make it look pretty. So now we are on R3 of x, technically the maximum value of it. So it's going to be the fourth derivative at x, x minus 2 to the power of 4 over 4 factorial. And we know that x is going to be in this range because they told us. And each of these pieces, we have to find out what their maximum value is. Okay, now I've already got the fourth derivative guy. He's this fella. Won't the maximum value of this fella happen when x is 2.5 or at 1.5, right? It's going to happen at one of the two extremes. And I don't care that the answer's big and negative, I just care it's big. I could save some work. What do you think? a 1.5 or a 2.5? Which one's going to get you the bigger answer? You could do both and find out. Well, I don't know. I'm trying my calculator. Barry's gone. 1.5 or 2.5? Which one would work?
1.5.
Right. Small things, big answer, right? That's essentially it. So I'm going to get 1 plus it, so it's like 2.5 to the power of 4. I can't do anything right now, so I'm relying on someone else to help me out here. What is this number? Because it's the guy that's going to go as the maximum value of the derivative. Somebody got a button in the calculators and do it.
I got it.
Okay, go for it.
Negative 0.1536.
So this piece is 0.1536. Why don't I care about the negative? Because there's an absolute value around everything. Okay, x minus 2 is coming up. X minus 2 to the power of 4. Its maximum value in this range. Well, if you plug in 1.5, you could plug in 2.5. I think it doesn't really matter, because I think in both cases, don't you end up with 0.5 to the power of 4? If you plug in 1.5, it's negative that. If you plug in the other, it's positive. So what's 0.5 to the power of 4? Because that's going to tell me the maximum value of this piece.
0.0625.
Okay, which is 0.0625. And 4 factorial is just a fixed value. So 1 times 2 times 3 times 4, which I believe is 24. And we are just about done. Can someone tell me what this is to 6 decimal places? Evidently, they changed their mind from question to question. This times this divided by that to 6 decimal places. I'm hoping it's at least 0 point something. No, I'm pretty sure it's 0.0.
I only got 4 decimal places.
Okay, what did you get? 0.0.
0.0004.
So your number.
There's a whole load of
F-
there are a whole
F
load
to
of
the fourth?
digits there. Yeah,
We
there
should
should be a whole.
Excuse me. The
yes.
number that you guys got for F, or the fourth
This guy.
derivative, yeah, that should be negative 1.1.
The
There's a 1 here?
1.5 squared is the bigger one. It has a bigger
Okay.
magnitude.
Okay,
No,
because you've got
I agree with you. I got 1.1. We
yeah.
should have used 1.5 instead of 2.5 because of the absolute
Oh.
value. We care about the magnitude.
Small is big, of course.
Well, no,
Okay,
it
so-
becomes the 2.5 in the bottom because of the 1 plus that.
You're right.
Oh, I think
Right.
that's my problem. I didn't get the 2 in there. Okay.
Okay. So what's the question or the change? Is this 0 point or 1 point? Is this number correct?
I don't know anymore.
I don't know.
So what they did was they used the smaller number 1.5 and then they added 1 for it because 1 plus x. So they got 2.5 to the 4 with
Right,
on
and
the
it just
bottom,
by
which is what we got
coincidence
before.
it happens to be that number, right? So this is a 2.5. Is negative 6 over 2.5 to the 4 negative 0.1536?
Yes.
Okay, so we're good. So our problem is this times this divided by 24 is not that. If your calculator is telling you that, your calculator has been set up to round off to 4 decimal places. Because I can tell looking at that, that should be a really big, ugly decimal, right? Now, if I had a calculator with baddies, I wouldn't be so frustrated myself, but I don't, so I have to rely on you hitting buttons for me. So someone else get a calculator, and this is annoying me, and figure out what the full answer is.
Well, I mean, for me, it's the same thing.
I mean, all of that comes out.
Mine
Is
is
that?
set up to round to the 12th decimal place, and I still got the same thing.
Well, that is a downright dumb question. Why should they ask you for 6 if there's only 4? I just thought, you know, that times that over 24 should be really ugly, right? It looks like it should be. Evidently, it's not. So if you want 6 decimal places, I guess you get a couple of zeros. Keep WebAssign happy, right? Fill in with zeros if you don't have enough digits.